corrected trans-cinnamic acid. And I'm also going to print that as a PDF file. Into that same folder called corrected trans-cinnamic acid. I'll just get rid of the .spa, which stands for spectral acquisition, because this is PDF. So now I want to do a library search. Checking my library setup, I have the Georgia State Crime Lab and the Nicolay Condensed Phase Academic Sampler. Those are the right two libraries. I'm going to hit search, and it tells me that I've got a 52.96% match to E-cinnamic acid, 97% pure E-cinnamic acid. So that's not a great match, but at least it is a match to the correct compound, and it looks fairly similar. So I'm going to print these. I'm going to print them on separate pages. And that's going to be trans-cinnamic acid search. And now the last thing I'm going to do is this IR spectral interpretation, try to have it tell me what functional groups it thinks are present. And it thinks it's an aliphatic primary amide and an aliphatic hydrocarbon, and it isn't either of those things. And you can see that these peaks, there's nothing in that region where those peaks are. So that's not a very good result. So what I'm going to do now is I'm going to reopen the uncorrected spectrum. The original trans-cinnamic acid, because sometimes the spectral interpretation works better on the uncorrected. And in this case it isn't. The aliphatic primary amide and the aliphatic hydrocarbons are showing up, and it is in fact an aromatic carboxylic acid, not any of those things. The peaks aren't really in the right place, so why it thinks it's these two, that's open to some debate. I'm going to go ahead and print that anyway, just for completeness. And we're going to call that trans-cinnamic acid functional groups. So it's a little bit of a problem when you're trying to use the Omnic software to find out why the peaks are in the locations they are, when it doesn't pick the right functional groups. But there is a workaround. Since trans-cinnamic acid is in the library, we can go to Library Manager under Search Libraries, and we can choose the academic or the Nicolay Condensed Phase Academic Sampler, because we know that's the library it was in, and we can search for text and search for cinnamic acid. And it gives us the spectrum for E-cinnamic acid, 97% pure, and if we double click on that, it'll give us the spectrum. We can add that to a window. Window 5. So there it is. It's actually an absorbance, so I would want to change it from absorbance to percent transmittance so I can see the more normal spectrum. This one's run as a Nujol mol. These really strong peaks that you see here are actually sp3 carbon hydrogen stretching, but that's from the Nujol or the mineral oil that it's suspended in. So these can be safely ignored. And this peak at 1450 here that's fairly strong is the CH2 scissor from that mineral oil. So let's try doing a spectral interpretation search on the E-cinnamic acid from the library. And now it actually says that it's a trans-olefin. It is in fact a trans-olefin. That's one of the functional groups that's in there. But it also says it's an aliphatic primary amide. And it's obviously not, because there are definitely no peaks in that region for the aliphatic primary amide. The problem we're running into is that the carbon-oxygen double bond stretch is in the same region for an alpha-beta unsaturated carbonyl compound as it is for an amide. And it's using that as the key in telling it that it thinks it's an amide. Right? You can see that the peak here isn't there either. So all the places where you would expect to see the amide except the carbonyl function are not there. So we have trans-olefin and we have aliphatic primary amide, right? Here's the peak at around 950 for the trans-olefin. And if we were to click on the plus there, oops, sorry, on the eyeglasses there, it would tell us that we expect to see a carbon-carbon stretching vibration for a non-conjugated between 1680 and 1620, for a phenyl conjugated, which is in fact what we have, at around 1625, and it should be quite intense. And for a COCC, when they're both conjugated around 1600, we've got both, so it should be somewhere in that region. And then the stretching and deformation vibrations, right, for the trans double bond, we should see a peak in that 960 to 970 range for the, that's a bending mode of deformation. So here it is, this peak at about 909 for the vinyl group, 909, 900, 990. For the trans, we see a one peak at about 965. For the cis, we would see a single peak at about 705. Right. So we're looking for a peak somewhere in that 965 range in our spectrum to indicate that it's a trans-olefin. And it's not an aliphatic primary amide, so there's no point looking at that. So let's open up our spectrum that actually has the peak labels on it. The corrected trans-cinnamic acid. And we'll have to change our display limit again, so we start at 60 instead of 65. So those peaks are on scale. So we're looking for a peak somewhere in the 950-ish range. We have a peak here at 942 and a peak at 980. One of those is the trans-olefin. Probably this one at 980 because it's fairly sharp. The peak at 942 is a little bit broad to be that trans-olefin. So the 706 and 767, those are distinctive for a monosubstituted benzene ring. This peak at 980 is probably the trans double bond. There's just one of them. And then we've got 1630 for the carbon-carbon double bond stretch, 1685 for the carbon-oxygen double bond stretch, and then this is our broad OH stretch from the carboxylic acid that engulfs most of the spectrum. 1493 and 1578, those are the typical peaks for the benzene ring breathing mode. And then we've got a carbon-oxygen single bond stretch, probably here at 1287, because there's always that, as well as the double bond stretch. So there are some diagnostic peaks in there that will be useful.